Hi, good evening, everyone. Welcome to the problem solving session, week 9 of linear algebra through geometry NPTEL course. Okay. My name is Bhabya. I'm a PhD from IIT Madras. Okay. And as always, on Tuesdays, 6 p.m. to 8 p.m., unless mentioned otherwise. And speaking of which, the next week's problem solving session will probably be shifted. Okay, to later, but the exact announcement will come to you, okay, regarding that. Now, yeah, without much ado, let's just begin this time's topic. And so, last time's topic, okay, week 8, focused on vector spaces and subspaces. Okay, vector spaces and subspace. And what are vector spaces? Just to recall, well, vector spaces are just algebraic objects which satisfy certain properties, and you may have seen in the lectures, and there are 10 properties. There are 10 properties. There are 5 properties here and 5 properties here. 5 properties related to vector addition, and 5 properties related to scalar multiplication. Okay, 5 properties related to vector addition, 5 properties related to scalar multiplication, out of which the most important are closure under addition and closure under scalar multiplication. What does that mean? Well, if I have a V in a vector space capital V, okay, or let me call it S, in a vector space capital S, closure under vector addition means that if I have two vectors U and V, when I add them, I should get them in the same. It should the addition should belong to the same space of vectors. Okay, so that is called closure under addition. And closure under scalar multiplication again means that if I have a scalar k, okay, and I multiply k with a vector v, such that v belongs to the vector space, then k times v will be equal to which is nothing but kv, which will be in again in the vector space. It's closed both under addition as well as vector addition as well as scalar multiplication. And the most important property, the other most important property, is that it should have the additive identity element, which means that, okay, so this is one, this is one. The additive identity means that there exists a vector, I'll call it 0, okay, because usually it's a 0 vector. I mean, it's always the 0 vector, such that in V, such that if I add it with any vector V, okay, then I get V back, where this small v also belongs to the vector space V. Okay, so these, out of the 10 properties, these 3 properties are most important. Why? Because unless you have some very strange object, maybe let's say polynomials, or if you have some, some kind of strings over some different alphabets, and then you need to verify each property is in that case. But as long as what's given to you is a vector, they satisfy all the other properties like associativity, and commutative addition and so on. All the other properties are automatically satisfied by suitable vectors. Okay, usually it's satisfiable, except maybe like a inverse is also satisfied if you have identity. That's right. So that's why if you are given vectors, then these 3 properties is something that you should definitely test, okay, to be a vector space. Okay, now what it means is that if I give you vectors like, let's say 1 0, okay, and let's say 0 0, now the question is this a vector space? Is V a vector space? Can you tell me? Under the usual addition and scalar multiplication operation. They are already vectors. So and over reals, of course, r square.
Yes. These are the vector spaces because I mean it is closed under this addition. So if I take the addition of these two vectors, the result would belong to. But then the thing is that if I take the addition of the vector 10 with itself,
Addition
so if I take
inverse
the
is not
addition
there.
of 10 with itself, so that is not belonging to S, I guess. So no, this is not a vector space.
Okay.
Yeah, right.
No.
No, that's correct. Yeah, it's not a vector space, and because if it does respect closure under addition, okay, but it does not respect scalar multiplication, where scalar is over reals. Okay, so what I mean is usual vector scalar multiplication, which is over reals. So if I take, let's say, 5 times 1 0, I get 5 0, which does not belong to my original vector.
Even it is not, I mean, supporting following the addition, because if I take the addition of the vector 10 with itself, the result would be a 20.
Yeah, that's right. Yeah, that's right. Yes, if I do 1 0 1 0, good. Yeah, then I get 2 0. Even though I'm doing it with itself, so both are not respected actually. That's right. And but one property is respected, that is that it has the null vector, right? But still, it's not a vector. It's not a vector space. That means if I give you something like, say, if I give you, let's say, x 0 such that x is a real number. What about this? One is saying yes, it is a vector. Okay.
Yes.
Okay, Satinder is also saying it's a vector space. Okay. So yeah, let's test it. Let's check for let's see, closure under addition. Two types of closure addition. Let's see, if I take, let's say, an x0 and a y0 such that x, y are reals, I'll get x plus y, which is also a real number. So this guy belongs to V. Okay, it's closed under addition. What about closure under scalar multiplication? So if I do x0 times a k, where k is a real number, then kx0, this is also a real number. So this also belongs to the vector space. It's closed under scalar multiplication. Good. So finally, I need to say that there exists a vector, there exists a null vector, which when I add to it, I get the same vector back. That is also true because 0 0, if I add it with any x0, it I get the same vector back, and this guy 0 0 belongs to the vector space. So this is a vector space. Okay, now one thing you may see is that, okay, a vector space, okay, is of course a family of vectors, and it's usually infinite, possibly infinite, unless it's the trivial zero vector. Okay, it is a family of vectors which may be very large. However, in a lot of cases, vector spaces can be represented very succinctly. Okay, vector spaces can be represented very succinctly. Okay, for example, if I had this vector, right, x0 such that x is in reals. So if I try to plot it, okay, in r square, let's say, okay, if I try to plot it in r square, okay, then what do you have? Well, you have that this represents all the vectors that lie on the x-axis, right? all vectors that lie on the x-axis, right? So all vectors that lie on the x-axis, vectors lying on, or you can say parallel to x-axis. So what I can simply say is that is there a finite set of vectors, okay, let me call it B. This is a finite set of vectors such that vectors in B can generate the entire of this V. Okay, is there a finite set of vectors B such that B can generate entire of V? And what do you mean by generate? Using linear combinations. And the answer is yes. Okay. For example, in this case, B is 1, 0. Because on doing scalar multiplication, just give me any vector in this vector space V. On doing scalar multiplications or additions, I can generate any vector in this vector space. Is it not? Right? So therefore, okay, B is a set. Okay. Therefore, B is called a basis. Actually, there is one more condition, but try to understand this. Okay, B is called a basis for V. Okay, this is the general idea. But the actual definition of basis, we are not just happy to have a finite set. We want a minimum set, okay, minimum size set. Okay, so why and what do you mean by minimum size set? Well, if I give you a set, okay, of vectors v1, v2, v3, okay, and say that this can generate the vector space capital V. Okay, I say that. So does this form a basis? Is this minimum? What I need to do is check if, but say V3 is just 2v1 plus 3v2. So what does that mean? So using v1 and v2, I can generate even v3. So why you put v3 in that list? So even this is enough. So then you can ask the same question again. Can I generate v2 using linear combinations using 1? Let's say yes, then even v1 is enough. But let's say after this point it's not possible. Suppose v2 cannot be written as a linear combination of L1, V1, then basis is this V1, V2, because I cannot do a smaller set than this. Okay. Yeah.
I have a question at this point. So why don't we often talk about the non-linear combination of the vectors? Is this because this is the linear algebra, or
Yeah.
is there some other reason that we do not that we are not interested in knowing that? I mean, what can be produced by the non-linear combination of the vectors?
Yeah, that's right. I mean, if you talk about non-linearly generating points, then you are entering a non-Euclidean geometry. So that is not cleanly governed by the principles of vector spaces. Okay, so we are only therefore talking about linear combinations, because ideas like rank and things like, for example, even vectors, right? In non-Euclidean geometry, how do you even define vectors? That's a bit Of course, you can do that. I'm not saying you cannot, but you need to be finer in terms of what you are talking about. For example, do you mean that the Euclidean, the planes are, I mean, the sorry, the space that you are talking about is still Euclidean, and the geometry of the objects are non-Euclidean, or even the space is non-Euclidean. So things like that you need to manage. But I'm not saying that you cannot do that. You can do that, but that is outside the scope of linear algebra.
Okay.
Okay.
Probably manifolds, etc. I mean the mathematical structures like
Probably what?
Curves, manifolds, etc.
Yeah, exactly. And a lot of things related to complex analysis and analysis folks, they mostly deal with these kind of things. For example, if you're talking about these fluid dynamics, you still talk about vectors, but in a they define it. They work in a non-Euclidean manner. Okay.
Yes.
Okay.
Yeah.
Yeah. Okay. But yeah, at least in the course, we are only focusing on linear combinations. Okay. So now the V2 cannot be written as a linear combination of V1. So therefore, this is the minimum sized set of vectors that can generate the entire of capital V, this vector space. So this is what is called a basis. Furthermore, what does it mean that I cannot write it as a linear combination of V1? It simply means that these two are linearly independent, right? So therefore, basis, okay, B, okay, or I'll write it in terms of a definition. B is called basis if and only if, okay, firstly, B should span the vector space, okay, basis of B. B should span the vector space V, which means that on doing linear combination, I should be able to produce any, this idea of generation, okay, that is what is called spanning. Okay? And second point is that vectors in B are linearly independent. Okay. So this was about bases, vector spaces, and so on, and then finally we talked about subspaces. Okay, and S is subspace of V if firstly S is contained in V and S forms a vector space. Okay, great. So this is just a small recap that I wanted to do because the next things that I'm going to discuss critically depends on this. Okay, this time what we talk about is what is called the 4 fundamental subspaces of linear algebra. Okay, or a matrix, if you want, of a matrix, 4 fundamental subspaces. Okay, so we know that a matrix represents a bunch of vectors, right? So it represents 1, 2, 3, 4, 5, 6, 8, 9, 10. So this is a matrix. Okay. Now,
Excuse me, sir. Like,
yeah.
can we increase the dimension? Can we take 3 cross 4 to understand that part? Subspace.
Sure. Okay.
Like you have taken 3 cross 3.
I've taken 3
so
plus
concept
3.
will be more clear, I think.
Sure. We
3
can
cross
do.
4. Let's see.
Okay. And let's do 3, 6, 9. Okay. So this is a 4 cross. Yeah, actually, you're right. It makes sense. Right. So this is a 3 cross 4 matrix. Right. So we've already seen 2 ways, right, in the course. 2 ways to view the matrix. One is the row view, one is the column view, as I've told you guys prefer. And what you see is, okay, so now what you ask the question is, so already this looks like I have 4 vectors. Okay, this is one vector, this is another vector, this is another vector, this is another vector, right? So I have 4 vectors bunched up in this matrix. So since they are vectors, I'll look at the span of those vectors. Okay. So what I'll do is, okay, this is the first observation. Okay. So A is consists of 4 vectors, column vectors, and of dimension. Okay, what is the dimension? If you can see that, oh, okay, so rather, yeah, it's of dimension 3, right? Each of these vectors are of dimension 3. Now they have a certain span, right? Now I look at the span of 1, 2, 3, 4, 5, 6, 5, 7, 9, 3, 6, 9. Okay, and they'll of course span a vector space, right? The span of any finite set of vectors is a vector space. Infinite set of vectors is also a vector space, but the span of any set of vectors is a vector space. Okay, now this is a vector space. Now this is a very special vector space. Okay, and since it is spanned by the columns of the matrix, this is what is called the column space, which is equal to the column space of A. Okay, now of course we've seen this interpretation before. Okay, when we did AX equals B, okay, what we were trying to find was the those, so we were trying to find that linear combination, those set of scalars x1, x3 and so on till xn, such that the columns of the vector c1, c2, c3 can be combined, okay, linearly combined to actually yield B. Okay, but if these are columns, right, so so what I mean is, like, if 1, 2, 3, 4, 5, 6, 5, 7, 9, 3, 6, 9, and I have like x1, x2, x3, and x1 is multiplied with this guy, x2 is multiplied, okay, so I need an x4 also, okay, with this guy, x3 is multiplied with this guy, and so on. X1 is solely multiplied with this, so hence I have x1 times the first column. I hope that is clear. But what is this? This is just a linear combination, no? Of what? Of the vectors c1, c2 and so on. Is it not? It's a linear combination. So what when you say is equal to B, I'm asking whether a linear combination of c1 to c2 to cn is equal to B. What am I actually checking? I am checking if B belongs to the span of c1, c2, cn, and if yes, then what is the linear combination? This is what I'm asking actually. This is another way to view it. Okay, this is another way to view it. That is, if I'm given a system of equations, I'm checking if that the given target matrix, okay, the target vector belongs to the column space spanned by these vectors or not. So that this space is what I call the span of the columns of the matrix is what is called the column space. Of course, we'll see more things about this, but I just want to give a quick recap. Okay, there are more things related to it. Okay, the second thing is what is called the so I'll come to this second thing. Yeah.
excuse me, sir. Like what the example we have taken just now. One like column wise, I'm telling 1, 2, 3, 4, 5, 6, 5, 7, 9, 3, 6, 9. So if I'm converting into REF form, row
Right.
echelon form,
Right.
so what I'm getting, last row I'm getting is 0. So it means ki there are 2 non-zero rows.
That's right.
So it means ki that will be only 2 out of this 4. Only the first 2 columns will be the column space for this
That's right. No.
example. What?
They first 2 columns will be the basis, not
Yes, that I'm saying.
okay. Basis, not
Okay,
not the column space. Column space they'll still be contained in the column space.
Okay. This all will be the column space. Whatever the vectors are there, that will be column space.
Yes. Right.
Yes.
Okay.
Thank
So
you.
I'll do that in detail in the coming questions. So if I that is what I'll do in the later questions, that if I cancel out some of these, if I do elementary column operations, it is just doing linear combination across the columns, and if I do linear combination across the columns, I will not escape the column space because they will still be within the span of these columns. Okay, so it means that now if I try to eliminate some of the columns which are linearly dependent, for example, if you see 3, 6, 9 and 1 to 3 is linearly dependent, and if I add the first 2 columns, then I get the third column. So I can eliminate these 2 and form zeros, right? So it means only these 2 columns are actually generating, so which means that these 2 columns form a basis of the column space. Okay, so these things will come to soon. Okay, but now I want to ask the equivalent answer. Okay, so 1, 2, 3, 4, 5, 6, 5, 7, 9, 3, 6, 9. Okay, now the question I ask is a bit strange. Okay, that is that what if I considered each of these to be vectors? Of course, they are not vectors easily, because if I just say 1, 4, 5, 3, it represents 4 vectors, each which has dimension 1. But rather I'm going to transpose them. Okay, I'm going to find so if this is A, I'm going to find the transpose of the matrix. Okay, and then I'm going to do 1, 4, 5, 3 and 2, 5, 7, 6, 3, 6, 9, 9. Now, if you observe, the rows are changed into columns. So now they are column vectors. Now I can ask the same question. What about A transpose times some Y equals B? What if I solve this? Okay, and even before we ask this question, what if I look at these columns and look at the span of these columns? Span of 1, 4, 5, 3, 2, 5, 7, 6, 3, 6, 9, 9. Okay, so this is the row view of doing things. Remember the lines, the intersection of system of linear equations. Okay, the other way to do it would be to actually convert the rows into columns this way. Okay, and look at the span of these vectors, and of course again they'll span the vector space, right? And then you can again ask this similar question like this. Okay, what is the linear combination that gets to be, and so on, things like that. But this is also another special space which is called the row space. So if you take the set of vectors within the within the matrix, okay, the matrix actually represents the row space as well as the column space, and they are somehow interrelated. They might not have a nice geometric meaning to it, okay, at least between row space and column space. So they are sort of duals of each other, okay. But Now what you realize is, now we'll do the same thing. Okay, so this has basis. Okay, 1 2 3 4 5 6, right? So this is its basis. So what is the dimension? Dimension is 2. Okay, dimension of this matrix. Oh, okay, dimension of the basis, sorry, I'm sorry, dimension of basis is 2, okay, which is the number of elements in the basis, which is interestingly equal to the column rank. Okay, so if you do a Gaussian elimination here, you will get 2 pivot elements. Okay, now if I do now if I find, let's do a check here. Okay, let's try to find the linearly dependent columns here. Okay, so if I look at can you find the linear dependence, or should we do Gaussian elimination? Okay, let's do Gaussian elimination. Okay, so 1 2, okay, so the original matrix itself was, so if I do column operation, it means I'm doing row operations. No? So I can do row operations here, 2 5 7 6 3 6 9 9. So let me do Gaussian elimination on this. Okay, remember that if I do row operations on this original matrix A, it means I'm doing column operations on the A transpose. Okay, so and then I'll do, so R2, I'm trying to eliminate this one. Okay. Oh, I'm trying to eliminate this 2, sorry. R2, I do R2 minus 2R1. Okay, so what do I get? I get 1 4 5 3. I get 0. 5 minus 2 times 4 is minus 3, and here I get 7 minus 2 times 5 is minus 3 again. 6 6 minus 9 is 2, minus 2. Okay, and then I get 3 6 9 9. Okay, now I try to remove this guy, so I'll do R3 minus 3R1. So what do I get? I get 1 4 5 3, 0 minus 3 minus 3 minus 2, and here 0, and 6 minus 4 3 is 12 minus 6. Okay, 9 minus 3. Okay, oh okay, good, Ron. Let's verify.
Last one will be 0, I think. So second row, it will be not minus 2.
Second row will be 0, you mean? So, oh, okay.
Next, second row.
Second row of this.
Second. So 0 minus 3 minus 3 0, I think we'll get.
0 minus 3 minus 3 0. Let's quickly check that. 6 oh sorry, good. Okay, yeah.
And last row will be 0 minus 6 0.
0 minus 6 minus 6 0.
0.
Okay, good. So now can we do something further? Okay, now let me try to remove this guy. Okay, and by actually subtracting this, so let's do R3. In R3 I do
again minus 2, we have to make it 0, otherwise we will not get the answer.
Oh yeah, sorry, this will be carried over. Oh yeah, now it's clearly linearly. So plus 2R2, and then I get 1 4 5 3, 0 minus 3 minus 3 0, and 0 0 0 0. Now this is in row echelon form. See, you see the staircase pattern, right? This is in row echelon form. And what do you see? What is the rank? What is the row rank Row rank is 2 because there are 2 pivot elements. And what is the column rank here? Column rank was also 2. Well, it so happens that the row rank is equal to column rank is equal to 2. But it's not just in this case, the row rank is always equal to column rank. That is the first thing. Second interesting thing is, okay, just like I said that these two form the basis, okay, column of the column space. Basis of row space is these two. Okay. So what does it mean that row rank is equal to column rank? Since I said that the dimension of the column space is equal to the rank always, the dimension of the column space is equal to the dimension of row space. This is the reason why even when you do column operations, you will still be able to solve the system of equations. Even if you do the row operations, you'll be able to solve the system of equations, provided that you don't mix them. Okay, you on the same process, you don't start doing row and columns at the same time. Okay, now, okay, so this is all said and good. Okay, now we see the relationship between row space and column space. Now, finally, what we do is, okay, we visit homogeneous system of equations. Okay, that is that if I have an A, okay, let's use the previous A only, 1, 2, 3, 4, 5, 6, 5, 7, 9, and 3, 6, 9. Okay. Now, what does it mean to say AX equals 0? Okay, that is the question that we are saying. Not just that, what does it mean when AX is equal to 0? What are the X's that satisfies AX equals 0? Now, these, interestingly, I mean, these are of course vectors, but they also form a vector space. Okay, the proof I'll leave it to you. But these vectors, okay, they form a vector space. Okay, and this is exactly what is called the null space of A. Okay, and similarly, you can ask the same question in the A transpose. A transpose is this tall matrix, no? And you ask the same question: what is A transpose X equals 0? What are these X's that satisfy this equals 0? So this is nothing but the left null space of A. Okay, and now there are two important theorems in this week's lecture. First is what is called the rank nullity theorem, which says that the dimension of the null space plus the rank of the column space, so the rank is nothing but again the dimension of column space of A is equal to number of columns, and this is nothing but the rank of A, and hence it's called the rank nullity theorem. There is a row version also, which is that the dimension of the null of A plus the dimension of the column, the rows of A, which is again nothing but the rank. Row rank and column rank are always the same, and therefore this is the number of rows. Okay. Now,
sir,
yeah.
Can we take A transpose, like as you have mentioned, we have null space and left null space.
Yeah, sorry. Okay, yeah, null space of A transpose, or rather, I forgot to put a left null space. Dimension of left null space. Yeah, not null space.
Okay.
Yeah.
But sir, just one thing to add. So I was reading in the definition that in null space, we multiply it from the right hand side, Ax equal to 0, and in left null space, essentially it is the same thing. It is coming from what you have written there, that A transpose X equal to 0. But in the definition, they were writing it as, they are calling it left null space because they are multiplying
from the left.
from the left hand side. Right. So they are writing it as Y transpose A equal to 0 is the null space for left null space for A.
I don't think it will be much of an issue. That's what I think.
No, it's not an issue actually. We can just look at it from a different, from the same perspective, not introducing a new space, but thinking of it as some property of A only. Because when we are going to A transpose, our idea is completely changing because we don't know how A and A transpose interact or how they.
Right. Oh, okay. So rather, you're saying why the name left?
Right.
Oh, yeah. Okay. Yeah, that makes sense. Okay. Good. Okay. So the second important thing in this lecture is how these spaces are related with each other. Row space and column space, comparing them geometrically, I do not know a neat characterization for that, but there is a neat characterization instead for the row space, okay, and the null space, okay, and the column space and the left null space. Okay. Oh, and by the way, these spaces are what are called the four fundamental spaces. Now, because every matrix describes these four vector spaces, and now the interesting thing is that they are orthogonal components of each, or orthogonal complements of each other. What it means? What does it mean? What does orthogonal complement mean? So if A is equal to B transpose, then B is orthogonal complement of A. So what this means, obviously, because of this definition, is that row space of A is equal to null space transpose. Sorry, or orthogonal. Not transpose, but orthogonal complement. But what does it mean? Okay, of course, this is in terms of matrices, but what does it mean here? It means that any vector I take from the null space is orthogonal to a vector in row space. Okay, so, or in other words, what does that mean? Row space of A is equal to all those vectors, okay, such that vector, when I take the dot product with any vector in the null space, I always get 0. This is what it means when two vectors are orthogonal, right? The dot product is 0. Similarly, column space is nothing but the left null space, orthogonal complement of left null space, which means that, okay, and what is left null space? Nothing but null space of A transpose, right? Null space of A transpose, which means that column space consists of all those vectors which are orthogonal to each other, to every vector in the left null space. So there is this diagram that was drawn in the lectures, you know that. Oh, okay. No, and finally, the final nice thing to note is that suppose W and W perp, okay, are subspaces of a vector space V, then any V vector in the vector space can be uniquely represented as V equals V1 plus V2 such that V1 belongs to one of the vectors and W perp and V2 belongs to the orthogonal vectors. Are not just subspaces, they are orthogonal. V2 belongs to W perp. What does this mean? That I can also write V as V1 V2, V1 plus V2, where V1 is in the row space and V2 is in the null space of A. I can also write V1 or I can also write V as V being in the column space and V2 being in the left null space. So this is the interesting thing, and any vector is consisting of components that are perpendicular components that come from, say, the row space and the null space, and combining them I get the vector V. I can write them, not only can I write them, I can write them uniquely, and these two spaces are perpendicular to each other. So you can imagine, like, let's say I have a vector, okay, in, say, I have a vector. So let's say I have a space where I have one plane, okay, I have one plane and I have another plane which is perpendicular to the other plane, okay. So, okay, and of course I'll have vectors which are lying on these planes, and I have another vector which are lying on these planes. Any vector I take from plane A, it will be perpendicular to the vector on plane B, and so if I take, and these are in, let's say, R cube, then anything in R cube, any vector in R cube can be written as a combination of this vector B vector times some scalar plus this vector, so some vector in A times some scalar. Okay, so that is the interesting property that we have. Okay, now that we've done with it, okay, that was a very long recap. So let's just directly attack this question. Question saying, for the matrix given here, okay, which A is 1, 2, 4, 2, 4, 5, 3, 6, 6, find the basis for the column space, row space, null space, left null space of A, compute the dimensions of each subspace. That's what it is saying. So let's just begin directly. Okay, you want to find the column space, row space, null space, left null space, each of their bases. Okay, now let's try that. A equals 1, 2, 3, 2, 4, 6, 4, 5, 6.
Excuse me, sir. Like,
yeah.
One doubt is there. Like, just now you have said that W1 and W2 are the W perpendicular are the subspace.
Orthogonal subspace.
Orthogonal subspace. So, can't we say that it is a basis for a particular vector? it will not a basis because since we are finding the any vector in that, so it will not form a basis means.
That is a good point. It should technically form a basis because they will always be linearly independent. But see, the question is, a basis will always be with respect to a vector space. Now I ask you the question, basis of what? You mean basis of V?
Okay. So means ki W and W perpendicular both are in the V. So it can't be basis, I think so then.
Okay,
Because
I get what you mean. But the problem is as follows. Okay, but that's a very good question. Very good question. I'll explain to everyone. Okay. What Satinder, no? Who asked the question? Satinder, no?
yes, sir.
Oh yeah. So I have a vector space V, and I have W and W perp, and they are both contained in V. Okay. Now, what Satinder is saying, which is a very good point. Now since I know that any vector in V can be uniquely represented as, and these two are orthogonal complements, by the way, can be uniquely shown to be V equals V1 plus V2 such that V1 is in W, V2 is in W perp. So now Satinder is saying that, so does that mean the set V1, V2 forms a basis, is a basis for V? This is what you are asking, no? Because any vector in V can be represented. Satinder, that's what you're asking, no?
Yes, I'm asking like V and V perpendicular will be basis, or V1 means ki V and V perpendicular whole thing can we treat as basis?
Oh, V perpendicular. What is V perpendicular?
W and W perpendicular.
Oh no. See, W and W perpendicular are vector spaces.
Okay.
Okay. I get what you mean now. Okay. I get what you mean now. W and so you mean W union W bar? You mean this forms a basis?
Yeah, W and W perpendicular, like from there we are taking the vectors. So because one of the vector belongs to the W and the another is W perpendicular, it means ki both will form the basis for the V. This I was just.
But you mean but since see W and W bar are not vectors, they are vector spaces, which means it's a set of vectors.
So vector spaces.
Do you mean you are doing a union? Do you mean you are doing a union?
Yeah. Something like that. I have the confusion.
So if you are doing a union, no, it will not form a vector space because these are vector space on their own, and they'll have several linear combinations within it. So, for example, W will have V, it will have 2V, it will have 3V, and so on. Okay, and it will have 4V1 plus 6V2, and so on. If V1, V2 both belong to.
You have represented like V vector as V1 and V2 now. So V1 belongs to the sum of the bases of W. I think it must be there. So
right.
V1 and V2.
Yeah, I just want to clear this first, that when I do a union between W and W perp, they will not form a basis because they'll have so many linearly dependent vectors. Because W itself has so many linearly dependent vectors because it's a vector space. And it has all linear combinations possible within W. Now, what you said was, okay, now the other part of the question is that any V, okay, can be written as a V1 plus V2. So, isn't V1 comma V2 going to form a basis of vector space V? So, that is another possible question that you may ask, right? Is this the question?
Yes, yes, sir. Yes.
Yeah, good. So, this will not form a basis because of the following reason. Because as I check for different V's, these V1s and V2s may differ, right?
Got it, sir.
Got it? So if I have a U, it will be V1 plus V2 and U belongs to the vector V. And then I have a vector V which is say V1 plus V3. And V belongs to the vector V. Now these, okay, fine. These two are linearly independent. I agree because they are orthogonal to each other. They can never be related. And you put V1, V2. But next, what do you do? Next, what do you see that, oh, V actually can be uniquely represented in a different way. V1 plus V3, not the same as V1 plus V2. Okay, or 2V1 plus V3 and so on. So now this V1, V2 is may not be enough to actually generate V3. So now you can ask questions like, can I put V3 here? And then try to continue this process. So, but something similar to the lines that you are asking is the following. The basis of W union the basis of W perp will be a basis of V. This yes, this we can say, because there is no confusion now. Using the basis, there is only one way to come up with things. Okay, Satinder, is this fine?
Yes, sir. Actually, I was asking this only, like in the row space, like when we have constructed the row space, in there must form some vector as a basis. And for the B perpendicular also, it has some basis. Now, basis of VW and basis of B perpendicular, if we are combined, so we can reach any vector, I think,
yes,
in B. So correct. This only I was asking actually.
Oh, you were asking about the basis only?
Yeah, sir.
Oh, okay. Then I think I just confused people.
No. You have explained very properly, sir. Not confused. Thank you, sir.
Okay. So, yeah. Okay. So yeah, okay. If this is meant what you meant in the beginning, yes, then yes. Their bases together will form a basis for V. Okay, and that's a nice thing, a nice way to see how the basis of V can be partitioned. But anyway, let's look at this question. So they are saying find the basis for column space, row space, null space, left null space. Okay, so let's quickly do that. Okay, find the basis for column space. Rowan is saying basis for row space is easy to see. Okay, then let's do row space first. Okay, let's do row space first. So for row space, I'll look at the rows, okay, and do row operations probably. I can see that so 2, 3, 2, 4, 6, 4, 5, 6. So the second column is just a multiple of the first column. I think that's what you mean, right? And next thing is there any other linear combination possible? But let's do Gaussian elimination to be extra sure. Okay. So this guy can be using Gaussian elimination. I can just do R1, R2. In R2, I'll do R2 minus 2R1, and then I'll get 1, 2, 3, 0, 0, 0, and 4, 5, 6. Okay, good. Now what I'll do is I'll remove this guy. Okay. Then R3, in R3 I'll do R3 minus 4R1, which will give 1, 2, 3, 0, 0, 0. 4 minus 4 is 0, 2 minus 8, 5 minus 8 is minus 3, and
minus 6.
Minus
6.
Yeah, minus 6. That's right. Okay, great. Now, is there anything we can do further? Well, to get in row echelon form, let's switch the rows and to the second two rows, 0 minus 3 6, right? So this is also a valid operation. Now I'll make this into 1. Okay, so what I'll do is R2 equals 1 by, oh, this is minus 6, no? Yeah, okay, 1 by minus 3 of R2. So what do I get? 1 2 3 0 1 2 0 0. Now it is in reduced row echelon form. So what do you have? We have that. Remember that we are doing row operations, but actually we are looking at the row space, which means we are looking at A transpose, column operations of A transpose. So this is a column of A transpose. This is a column of A transpose. So,
sir, this is not yet in row reduced, na? For row reduced, you have to like do one or more operation, and the pivot in the second column, all entries above it should be 0 as well.
Yeah. So this is in partial reduced row echelon form. That's correct. So to do that, we just need to do R2. I'll do R2 minus. Can I not do that?
We can do R1 minus R1. We will change R1.
Yeah, we need to change R1.
Yeah.
So we will do
R1 minus 2 times of R2.
R1 minus 2 times R2. Yeah, that's correct. Good.
So first row comes out to be 1 0 minus 1.
First row comes out to be 1 0
minus 1.
Minus 1. That's correct. Yeah, that's correct. Good. Thanks. Okay. And now it is in reduced row echelon form, right? Everything above the pivot is also 0. Yeah, that's correct. Okay, now it is in reduced row echelon form. Okay, and no matter the columns, the rows form the columns of A transpose. So therefore, the basis of and note that, okay. So this is important. Okay, so why is this the basis? Why is this the basis? Okay, why is this the basis? Firstly, note that when I do row operations, I'm simply doing linear combinations. If I'm doing linear combinations between the rows, I'm still in the row space. So what it means that no matter if I do linear combinations, if I do row operations, I will always span the same row space. Okay, that is the first condition of being a basis for row space. I will still span it. And the second condition is linear independence. And that is what Gaussian elimination tests, right? That these two are linearly independent with each other. And because the other row was linearly dependent, that's how we got all zeros. So therefore, what do you have? Basis of row space is 1 0 minus 1 and 0 1. Okay, good. So for column space, it's a similar process. Okay, but I think you can already sort of make out that if you add the first two rows, you will get the third column, and it cannot be that you will get the second column from the first column. So this is actually even easier to see. You cannot get the second column from the first column. Why? Because if I multiply the first by 2, then I'll get 2 4, but 2 4s are 8, but it's showing 5 here. I cannot hope to get to scalar multiplication and get the other. Okay, so the basis will still have two elements there, because I can see
like I think so you're calculating now for the column space, huh?
Yeah, column space.
So for column space, when we are applying RREF form, so we have to apply column wise.
You have to apply column wise, but I mean that might personally I find it a bit confusing. Yeah. See, personally I find it a bit confusing. So what you can do is instead do Gaussian elimination on the transpose. Okay.
Yes, sir. Yes. Yes.
So personally, I find this more elegant, and you can do that. I'm just doing a very layman kind of way, that I'm just looking directly at the telling. Okay, but yeah, if you want to formally do it, then you need to do Gaussian elimination. Okay. And if they were asking just about the dimension, then you know that the dimension of row space is equal to the dimension of column space. So therefore, it will again be 2. Okay. Now the null space. Okay. Null space.
So, like, since it is 3 cross 3, so that's why it will be row space and column space dimension will be same. But I think if the order is something m cross n, then the dimension will be different, no?
No,
then it will not same.
No, that is not true. It will be same.
And row space and column space dimension will be same. I think no. If it is 3 cross 4, I think it will be like column space will be in the 4th dimension, and row space will be in the 3 dimension.
No.
If I'm taking 3 cross 4, it means ki I'm mapping from R3 to R4, R4 to R3.
Yeah, see, I'll tell you. Okay.
Okay.
What is the so for example, if I have a matrix like this, okay, which is 0, 1, 2, 3, okay, and 4, 5, 6, 7, and they look to be linearly independent with each other, right? They look to be linearly independent with each other, and yeah, they are linearly independent. Now I ask you, what is the dimension of what is the okay, or rather, I'll give a very simple one. Okay, if I give you this, the matrix itself is 0, 1, 2, 3. Okay, the matrix itself is 0, 1, 0. Okay, the matrix itself is 0, 1, 0. Okay, this is the matrix. That's it. Now I ask you, what is the column rank? Now you'll say, oh, column rank is of course 1, because there's only one column. But row rank, if I ask, then what you mean to say is the row rank could have been 3, right? Or it can't be 3, of course, because I have 0, 1, 0 here. But let's say I have 0, 1, 2 here. This still does not make sense. But I think I need another vector to actually demonstrate this. 1, 0, 1. Okay, yeah. Now you'll see that the row rank is 2. Right, the row rank is 2. What is the column rank? 2. It's still matching so far. But why is this matching? For example, let's say I make this 1 now. What is the column rank now? Column rank, the second row cannot ever be produced by the first row. I hope you can see that by multiplication. So column rank is still 2. And what about row rank? Well, the third row is a multiple of the first row. Third row is a multiple of first row. So therefore I can eliminate this. So the row rank is also 2. I hope you can see the trend. Now why is this happening? Because if I plot this, okay, if I plot this on a graph, this particular bunch of vectors, even though I get what you mean to say, Satinder, that this is a 3-dimensional vector. Okay, this is a 3-dimensional vector, and these are 2-dimensional vectors. But we do not mean dimension in that sense. We mean dimension of the span. What are the things that it can reach? Okay, that is what we are trying to say. So what does it mean when column rank is 2? It means that if I plot these two vectors, Okay, if I plot these two vectors on 3D space, for example, 0, 1, 0 is, let's say, this, and 1, 0, 1 is, let's say, this. What does it mean? It will span a plane, is it not? A plane is an object of dimension 2. Now, if I look at the rows now, okay, that was a column way to see it. Now, let's look at the rows now. The rows are 2D objects, so I need to plot it in R square. Now, what do I have? I have 0, 1 here. I have 1, 0 here. Okay. And again, I have a 0, 1. So I don't need to plot that. But this forms a basis for R square. So it is able to generate any vector in R square. So what is it going to span? It's going to span the entirety of R square. What is that? A 2-dimensional vector. So I get it. What you mean is that it will seem like if the matrix is of a strange dimension, okay, like a very fat or a very tall matrix, it seems like one of the components has a very large dimension. Okay, has a very large dimension. But the fact that the matrix is also thin is causing a problem. It's causing a problem in the sense that you are not actually looking at the dimensions as the number of coordinates, but rather you are looking as the dimensions as the amount of area that it can reach, okay, which in this case is both planes. So if you have a matrix and then you plot the row space and column space, you'll still get the same object. I mean, you'll still get a plane. Okay, that's what it actually means. Okay, yeah, Rohan, that's right. Confusing the word dimension with coordinates. Dimension can be of space only. Vectors don't have dimension. Well, I mean, you say an n-dimensional vector, right? I think that is where the confusion is, because you have dimensions. You have dimensions in vectors, but what you're talking about is not the dimension of the vector. You're trying to find the dimension of the vector space, the span. Okay.
Right, sir. But when we say that suppose x is an n-dimensional vector, to refer that x is coming from Rn, so still we are talking about that space itself only. So we are saying x is an n-dimensional vector. So it is coming from Rn.
X is an n-dimensional vector means that the vector lies in dimension. So it has some kind of property, no? It's still a property. Of course, I mean, if we get into the semantics of things, then, I mean, you can again say that, that n-dimensional vector, maybe I can reduce it to, sorry, I can increase the dimension and look at the same vector and so on. But yeah, okay. I mean,
we both are saying the same thing actually. So yeah, basically the semantics and all.
Okay. Yeah, Kishore, you have the address.
Just to continue that, see, when we say n-dimensional, where n is equal to 3, n is equal to 3, is that mean we have the plane in 3-dimensional vectors? I mean, like a coordinate plane?
Exactly. So yeah, so if I have a 3-dimensional vector, that means to describe the vectors, I need at least 3 components.
Yeah, I mean XYZ axis.
XYZ. Yeah. So that means that I need a 3D plot. Okay. So the coordinate plane should be 3-dimensional. You are right. Yeah. To describe it.
Okay. So this is with respect to the n-dimensional vector. But whereas when we are saying the dimensions of the rows and the columns, right? So is that same relevant to this?
Absolutely. So because look at the example that Satinder was actually motivating, that if you look at the row space, it is the space vector space spanned by the rows, and the rows are 2-dimensional vectors. Right, Kishore?
Yeah.
And the columns are 3-dimensional vectors. Now you can ask the same thing. You can ask, of course, that okay, they are 2D vectors. I can still plot them in 3D, right? You can say that, but I could do that, but it's a bit redundant because anything I plot will only be on this plane and not go deeper or nearer to us, right? It will only be on the XY plane.
Yeah. So that's clear for me now.
Yeah.
So when we are trying to evaluate the row dimensions and then column dimensions, right? So what is the significance if you say like the same data we are putting into 2-dimension the coordinate plane, the same data we're putting in when we are taking it into rows, right? We are putting into 3-dimensional coordinate plane.
Yeah.
So the significance, what we are trying to achieve by this?
What are we trying to achieve by this? Well, see, we are trying to get a proper. So, are you asking for applications?
Yeah, applications are. Let's suppose the data is going to be remained same. That's for sure, right? So, if we take some matrix, the data is same, but we are putting into 2 different dimensional weaving.
That's right.
The exact view we are trying to view in 2-dimensional as well as in 3 dimensions, as per the number of rows and the number of columns, right?
That's right.
So when we do this, what is the resultants we are going to get? I mean, of course we are putting, but there should be some reason to put those coordinates into such dimensions, right?
Well, I don't exactly understand.
Hope my question is clear because probably I may be deviating from this, but
No, it's okay.
I'm not sure, but what I'm expressing is rightly reaching to you.
No, I mean, yeah, that's okay. I don't think it's a deviation. So my question is like, are you asking for an application or are you asking for a?
Yeah, we can take an application. Yeah.
Well, we have cases where I think maybe, for example, an application would be maybe you use this in data science a lot. If you,
sir, I can think of one application.
Yeah.
So suppose we have a very big rectangular matrix, let's say 50 by 5 million. So in this matrix, 50 by 5 million, apparently it might seem that we need 50 into 5 million integers to store. But someone can come up and say, if we only look at the 50, if we only look at 50 columns, I don't know which 50 columns, but and if you just and if you throw out all the 5 million minus 50 columns, which are huge, so instead of storing 5 million columns, if we can store only 50 columns, the rest are linear combination of them. So at first, this statement is not pretty intuitive. It is very counterintuitive. That how can, but it will happen as number of linearly independent rows and number of linearly independent columns is same. So at most 50 only can be there. 50 columns can be there, which are significant.
See, Rohan, I have a problem with that application, and that is that the number of possible linear combinations are infinite. And how do you find the set of you find sort of the basis, okay, let's say, and you want to generate the data back. So what you are saying is a sort of a compression, right? That I have a large matrix. Yes,
excuse me, sir. Like what Rohan was saying, I think that will be depend on null space, because on null space the dimension will be lost, I think.
Just 1 minute. Okay, sir, I got your point. So you are saying that to get back the original matrix, I'll still need the coefficients, right?
No. So what I mean, okay. So what are you storing exactly? You mean you are storing the basis vectors?
Actually, it is basically why am I doing it? So
no, but what are you storing? What is the operation that you are doing?
Right. So So as I
Just
told
one
you,
second, Rohan, one second.
Yeah, go ahead.
Sorry to
Go
interrupt.
ahead.
Sorry to interrupt. Just I wanted to clarify one thing.
Yeah.
See, of course, your application, I got to I got to understand that, because what you're trying to say is, let us not take 5 million, let us take just 100-dimensional data. So what we wanted to say is, we don't want to see 100-dimensional data. That's the reason we remove few of the columns. That becomes 50-dimensional data, so that it can be understandable for us, for the human brain. So that's what you say. That's of course one way of doing. But the case here is, we are trying to transpose the data, and then we are having the same data. We are not losing any data here. In this case of matrix, see 0 1 1 0 0 1. Of course, if we remove the data, then it has to, we are losing the data. But here we are not losing the data. We are not removing any data, but still we are living in the same 2-dimensional and 3-dimensional data. I mean, like vector space, coordinate plane. So I think, Babya, last time we have spoken, right? Few applications for the machine learning applications. Hope you remember.
So I have a point at this point. What Rohan says would probably resemble to the decomposition of the matrix, like say
PCA, right? What you are saying is PCA.
Yes, or PCA or SVD or any other kind
Or
of
maybe CR decomposition.
wherein we find the most prominent thing at the cost of some. We may lose something, but then by and large we would be getting the prominent chunk. But here the question of Kishore is something else.
Okay. I mean, that's
So here in this case, right, we are not losing data, but still we are trying to put into 2-dimensional, 3-dimensional.
Okay. Yeah, Mr. Shiv Kumar, you're raising your hand. Do you want to speak? Hi, Mr. Shiv Kumar. Yeah.
In network analysis, are you able to hear? Are you hear now? Yeah. In network analysis, we get a similar situation wherein for any network, when the nodes are determined, we calculate we write what is called incidence matrix and augmented incidence matrix. Augmented incidence matrix considers the reference node also. But when we solve the network, we don't consider one row, which is, we know that it is a linearly dependent vector on the other vectors, that is the reference node. We simply neglect that and form what is called reduced incidence matrix, having one row less than the augmented incidence matrix, and then solve with the understanding that this reduced incidence matrix is a linearly independent matrix. I think here you are facing a similar situation where the rank is less than the order of the matrix. Am I right?
I mean, does that is it in lines of what you are?
What I mean to say is, in this theorem 5.1 in the book, let A1, A2, A3, N be linearly independent n-to play of vectors in Rn. Then A1, A2, N is a basis of Rn. Then when he proves, he assumes starting that Z is 0. That means A1 is considering as U1, rather column vector I'm reading, U1 and Z1. Z1, he takes it as 0, and then the vectors U1, etc. UN in Rn is linearly independent. And if summation of j is equal to 1 to n, Cj Uj is equal to 0, then sigma, same sigma Cj Aj j from 1 to n equal to 0, then Cj is equal to 0 for all j. Since theorem 5.1 is true in Rn by assumption, U1, etc. Un is a basis for Rn. And so un plus 1 equals j sigma summation j1 to n tj uj for contains scalars tj. It follows that an plus 1, that is a vector, page number 241, is summation of j was equal to 1 to n tj aj. This is impossible. So the assumption for all that zj is equal to 0 must be false. Some zj is not equal to 0. And by numbering the aj, we get zn plus 1 not equal to 0.
Yeah, I think that we got a little lost in the process. I mean,
what I understood is that since here the rank is 2 and the order of the matrix is 3, that means rank is not 3, you are able to get a 2-dimensional vector that is a plane. Am I right?
That's what Kishore. I just want to ask. I mean, is this along the lines that what you're asking about, or?
See, the case is here. What we are trying to do is we are just transposing the matrix, and then based on that dimensions, we are trying to plot it onto the coordinate plane, right?
Sir, excuse me, sir. Like I have a little bit doubt here.
Yeah.
Satendra, let one finish actually. Otherwise, it will go like very randomly. So let Kishore finish and then you say. Okay.
So here, let us suppose the rank when we say, is this the same rank? Column rank, array rank is equal to the rank what we have discussed in the previous classes, which is n number of unknowns to the pivot table. Is it the same thing we are referring to, or is it two things are different from that?
Unknowns. See, the rank we were talking about was the number of pivot elements in the reduced row echelon. It's the same. That is correct.
It's the same. Yeah. So here row rank and then column rank are referring to the same the topic or explanation.
Exactly. So
in that case, right? Probably this kind of plotting of transposing the matrix and then plotting the two-dimensional. Of course, when we based on the data, sometimes the row might the number of row might changes to the columns, and then the column changes to it might be not equal always, but it might be unequal. So in that case, right, probably what I'm missing here is the purpose of doing this. Of course, if we are doing something in the mathematics, it should have a valid reason at the background. So what I'm missing is the purpose of doing this way to plot.
Oh, but see, one application, I think at least, I think Rohan was stating this same application that
not even as per the real-time applications, but even when we think mathematically also. So we are not getting the exact purpose. Of course, if we are doing some row operations, what we are trying to get is to get the pivot element.
Yeah.
So here when we are trying to transpose it and plotting those data onto the coordinate system, so there should be some background purpose to achieve something.
So see, the interesting thing is that no matter whether you are transposing it and plotting it, or whether you are plotting it right away, which means that you're looking at it in the row way and the column way. If you are trying to solve a system of equations, the linear combinations will act in a similar fashion. What do I mean by that is, when you are trying to find a set of unknowns x, y, z, it so happens that if you plot it, if you look at the set of linear combinations that lead us to that particular target vector, it is consistent if it is consistent in the column space wise, and it is consistent if it is consistent in the row space wise. So this is the direct understanding of it. I mean, see, this is, of course, this is not the only application that is there. I mean, if you're looking at mathematical application, just mathematical application, for example, you have you do have row rank, column rank, and so on, but you also have null space, right? Dimension of null space. For example, null space is a measure of the consistency of the system of equation. Okay, and you already have that the nullity, okay, which is the dimension of the null matrix. If you sum it up, okay, if you sum it up with the row space, the dimension of the row space, then you get a number of columns. Now, what you can, I mean, similar to the application that Rohan was saying, that if instead of if you have a very large amount of data and it's a very dense matrix, what does that mean? That it means that if it is likely that a lot of them are linearly independent from each other. A lot of rows are linearly independent from each other. Then why don't I consider the null space? I compute the basis, the null space and the basis for the null space, and then try to do something with the null space. Okay, so I mean, an immediate application you may not see, but these are very fundamental things that will be used all over the place under the covers. Okay.
Okay.
Yeah, but okay. So Satinder, you were saying something that, right?
Yes. I have a little bit confusion here. Like you have said, the dimension of row space and column space will be same. It means that both have the same basis. Number of bases will be same,
Correct.
Not exactly same. So number of bases will be same.
Number of elements in the basis.
Number of elements in the basis.
More than one basis. There could be infinite bases. Yeah.
Okay. Now the one more thing is there, little bit confusion.
Yeah.
Like if I'm going with the rank nullity theorem. So rank nullity theorem means ki dimension of column space plus dimension of null space is n. Means if it is m cross n means it will be n.
Correct.
So I can say like this also, dimension of row space plus null space will be also n.
No, the dimension of row space plus the dimension of the left nullity.
No, because as you have said, ki dimension of column space and dimension of null space is same.
Yeah.
So I can replace the dimension of column space by dimension of row space.
So
examiner is going to direct the marks.
That is correct. But the summing up part is the problem. So here you have, because you need to sum it with the left nullity. Okay.
No, sir. Actually, I think the rank nullity theorem tells us that rank plus nullity is that number of free variables or n, whatever it is. So rank, anyone can write it as dimension of row space as well as dimension of column space, because rank means both.
That's right.
So
That's right.
Inder is trying to interchange dimension of column space with dimension of row space, and he's free to write, right?
Yeah. I mean, in the way that that's correct. I mean, because the rank are anyway always the same. That's right. So just that. Yeah, actually, I wrote it in a confusing sense. It need not be.
No, sir, but what you said, I got your point. That is very much useful to find the dimension of left null space. That way of writing it. Otherwise, how someone will obtain the dimension of left null space?
Exactly. I mean, if you just have, like, if you're just talking about column space, then going to left null space is a bit of a jump. That's all. But you can equivalently just remove this part. Okay. And all the number of rows and number of columns actually depends on is just the dimension of the null space and the dimension of the left null space. Is that fine, Satinder?
Got it, sir.
Okay, great. And yeah, going back to it, Kishore.
I think still I am discontented. Of course, that's not a problem.
That's fine.
We can discuss this because this is taking much time. I think this needs more time to understand.
Sure,
we can continue with the problem. So,
okay. Yeah. So the question says compute the null space. Okay, and did we end up computing? No, we did not end up computing. Okay, so it says compute the null space of this particular matrix. Okay, and I'll just be quick about it. 1, 2, 4, 2, 5, 5, 3, 6, 6. 1, 2, 4, 2, 5, 5. 2, 4, 5. 2, 4, 5, 3, 6, 6. You are asked to compute the null space. Now, what is null space? Null space has two properties. First property is that null space is orthogonal to the row space, right? That is one property. But to find the null space, it's a bit, it may come in handy or not. And the other way to find it is by using the main property of null space, that it is the set of equations that satisfy the set of x's that satisfy this. So all you need to do is now 1, 2, 3, 2, 4, 6, 4, 5, 6 times x1, x2, x3, all those x1, x2, x3 that satisfy this equation, right? So that is null space. It's also called the kernel. Now, we have already reduced it to row echelon form, so we can just directly use this because Gaussian elimination, as you know, can be used to solve system of equation because of the fact that the solution is not affected. So I can write it as equivalently this, okay, x1, x2, x3 equals 0. So what do you have? You have x1 minus x3 equals 0 and x2 plus x3 equals 0. Then what do you have? You have x1 equals x3 and x2 equals minus x3, right? So let's parameterize this. Let's say x1 equals s, okay? Then what do you have? You have x1 equals s, x2 equals minus s, or let's write t.
Sir, it should be 2x3, na? x2 equal to minus 2x3.
X2 equals, yes, minus 2x3, that's correct. So this is minus 2x3, thanks. Minus 2x3. So what does it mean? x2 equals minus 2t and x3 equals t. So t times 1 minus 2, 1. Okay. These set of vectors okay form null space. This is the null space. Okay. And what is the dimension? Dimension is equal to size of the basis, right? Dimension is the size of the base. Yeah, you're saying something?
One dimension.
Exactly, one dimension. Because the basis is, which is 1, since basis is just minus 1, 2, 1. The size of the basis is 1. Okay? So dimension is 1. Now you can verify the rank nullity theorem, right? So if you do 1 plus the number of columns, the column rank is 2. So what do you get? 1 plus 2 is 3, and you get that the number of columns is 3. Okay. You can further do an interesting thing. You can actually multiply this with anything in the row space. Okay. And you should be getting 0. By multiply, I mean dot product because it's orthogonal. let's see if that is true, whether we did any mistake or not. Okay, for example, the row space will have 1, 2, 3, right? So let's multiply that. So 1, 2, 3, not multiply, sorry, dot product. Okay, a dot product of 1, 2, 3, and 1 minus 2, 1.
0 is coming.
You should get 0. It's coming to. Why am I writing 0? It should be coming to 2 minus 4 plus 3. Oh, why am I getting 2? It should be 1. Okay. See. Pick anything in the row space, it will always be orthogonal to it. Okay, so you can also think of row space to be a plane, okay, and the normal to the plane, okay, is the null space. Well, the normal need not be a single vector, remember that, okay. It could be another plane if you are talking about higher dimensions. But that is what I was talking about. You show that if the plane that you have is highly, it has a high rank, which means that there are too many linearly dependent columns, okay, independent columns. So then what you have by the rank nullity theorem, this the null space is actually very low dimension. So you can remember the null space instead of remembering the. So this is a nice dual property that you have, which I think will have several applications. Okay, in practice. Great. So let's quickly. We have 15 minutes left. So let's tackle the other questions. So the question is saying, okay, question 3. Maybe we can do 2 questions. Okay. Try your hand at this, okay. Suppose A and B are, this is simple, okay. Suppose A and B are m cross n matrices such that row space of A is equal to row space of B. Show that the systems Ax equals B and Bx equals 0 have the same solution set.
Sir, two row spaces are same. That means by performing elementary row operations, A can be converted into B, and the vice versa. And elementary matrices are always invertible. We know that fact. So suppose capital E be the elementary matrix, which if we perform on A from the left hand side, EA is B. We can write that because row space of A equal to row space of B. So directly we can write EA equal to B.
That's right.
So Bx equal to 0 in turn will give us Ax equal to 0 because E is invertible. So we'll just put him on the right hand side, and from Bx equal to 0 we can directly jump to Ax equal to 0.
Yeah, good. Good. Is there an alternate way to do it? Can you think of one? That is right. You are analyzing the. Yeah, Mr. Sugar.
From this question, it appears that B is equal to A transpose. Is it right?
From this question, B is equal to A transpose. Okay, I do not see it immediately.
No, sir.
Because Ax equals 0 and Bx equals 0 have the same solution. Is it possible that B is A transpose?
I mean,
maybe a very rare scenario, or maybe a very particular one.
Yeah, in a very particular scenario, I agree, because row space of A is equal to row space of B. For example, what you can do is you can trivially take B equals A, and this will still be satisfied. But A need not be A
Because in
transpose.
today's class, when you have to analyze spaces, Ax equals 0, you start with A transpose Y, no?
Yeah,
And then you find a column space which is actually row space.
yeah. That was to do row space. That's right. But we are talking about both being row space. If you are saying if we were saying column space of B, then yeah, something like that could be true.
Okay.
I'm not totally sure, but yeah. But since we are talking about both being column, I need to transpose A also, transpose B also to do computations. Okay. And yeah, this may not generally be true because this is not generally true because I can simply take B equals A and these conditions are satisfied. Row space of A is same and Ax equals 0 and Bx equals 0, but I can take A to be a non-symmetric matrix.
So B can't be A transpose.
Yeah.
Or sir, we might take A and B any invertible matrix. Then also it will be same thing. A and B take any invertible matrix. The row spaces are Rn actually.
A and B both are invertible.
Right, square invertible matrix.
Right.
If you think of it. Then the row space will be Rn or Rm in particular. Rn, right?
That's right.
So I'm talking about a very special case again because M is equal to N. So I'm making them square matrices again.
Okay.
So if M is equal to N and A and B are invertible, then definitely Ax equal to 0 will have solution. Only solution will be trivial solution. X1 equal to 0, X2 equal to 0, and everything is equal to 0. Same as Bx equal to 0.
Sure.
But if we take the rectangular one and so you are asking, can we do it in some other way?
That's right.
Without introducing elementary row operations?
Yeah.
We can actually, but that will again need us to perform row operations on it. And now there are two ways.
Either I can tell the solution
and do the row operation, or I can pretty much write the row operation. Like I can reduce them in some. But essentially, I'm doing the same thing. I'm multiplying it on a matrix.
Yeah. If you can think of it in terms of row operations, I agree. You can think of it in terms of rows, but see, you can always think it in terms of rows in a sense that if I look at A and I'm saying that the row space is same, so the span of the rows is same as the span of the rows of B. And if I do elementary row operations, it's never going to change it. And elementary row operations can eventually help fixing Ax equals B and Bx equals 0 and lead to the same X. That is the underlying principle. And that is one way to do it, correct. But the other way to do it is simply using the knowledge that we have of vector spaces. Okay, I know that the orthogonality. Okay, I know that row space of A, okay, is the orthogonal complement of the null space of A. Right? Is the orthogonal complement. What does orthogonal complement means? It's complement with everything there. But additionally, I also see that Ax equals 0 and Bx equals 0. But what did I say? Ax equals Bx equals 0. All the x's that satisfy this relation, okay, for A, let's say, all the x's that satisfy Ax equals 0 forms exactly the vectors in the null space. Which means when we talk about the solution set for this Ax equals 0 is nothing but the null space. Okay. Now, you have a row of A equals null space of A transpose, which is equal to the solution set of A. Now, you have row of B is equal to null space of B transpose, which is again the solution set of B. But these two are equal according to the question, which means row space of A is equal to So okay, so sorry, it should go in the other order. So these two are equal according to the question. Row spaces are same, so it means that the null spaces are same. And since we are talking about the orthogonality also, that will also be preserved, and therefore the solution set of B is same. Okay, orthogonality.
Sir, can we write solution set of Ax equal to 0 to be clear?
Yeah. Sorry, this is confusing. But this is clear, right?
Right, yeah. And yeah, that's a good proof. I didn't think of this. Nice.
Yeah. So I mean, this is a shortcut way to do it, but this gives a deeper understanding. The first one that you suggested actually gives a deeper understanding. Okay. Yeah, Kishore.
Yes, sir.
See, I think based on the question, row to row, row of A, row of B is equal to, he has given the condition. In that case, of course, we accept it. Then extending this, I think as row of A and row of B are same, even if we put into column-wise matrix of the same, then column A is equal to column B. Is it would be right statement?
No. If row spaces are same, column space are same, it need not be true. That's what I think. Not totally sure. Yeah, I don't think that is true. For example, let's say I take 1, 2. Okay.
So just a small hack here. I just maybe it's a wrong hack. See, when we have 1, 2, 3, 4 as you've taken, okay, you can add one more row.
Yeah, that's so. Okay, let's slightly increase. Okay, into avoid
make it a non-matrix, non-square matrix.
Okay.
So here, what is the 2 by 3? So it's the same when we say row of A is equal to row of B, then the same thing would be reflected to B as well.
Same thing would be reflected to B.
For the question condition.
Okay, yeah.
So if you make this put into column space, then we can transpose this, right? We can
you can transpose this and then work with it, but you will actually be working with rows only.
Yeah, of course we are working. At the background we are working with the rows, but at the forefront we are making it transpose, and then we are.
Okay. I get what you meant. So you mean the question is instead asking column space of A and B are same, and now what you're going to do is you're going to transpose them and say that row space is same, and then work with it. No,
but if they say row space is equal, then vice versa, it should be column space also should be equal.
But see, the thing is, as soon as you've transposed them, the proof that will follow is not that null space of A, null space of B. It will be null space of A transpose, null space of B transpose. And what is that? Left nullity. So if column space of A is equal to column space of B, then what you have, left nullity of A is equal to left nullity of B.
Okay. But the solution sets will be same.
Solution set will be same, but solution set will be same not for Ax equals 0, which the question is asking. It will be same for A transpose x equals 0.
Okay.
And this is nothing but left nullity. Okay. So yeah, that is where the modification will happen. Good, nice. I think Rohan has given a counter example. Let's see. A is 1 0 0 0. B is 0 0 2 0. Okay. So
row space is basically
row space is the same,
but the column space is different.
Column spaces are quite different. That's correct.
Perpendicular actually. Orthogonal complement.
Yeah. Good. Nice. Good. Yeah. Column space is quite different. That's right.
Can you just explain this?
So the question that we were asking was that if row space of A is equal to row space of B, does it imply that column space of A equals column space of B? This is a natural question to ask. I thought this was what you were asking in the beginning. If you look at row space of A, and row space of A is what? Everything that is spanned by 1, 0. The vector 1, 0. No, what is vector 1, 0? It's just the x-axis. So row space of A is just the x-axis. Okay. And what about 0, 0, 2, 0? Well, this is also x-axis. Because I can multiply 2, 0 by half, a scalar half, and then work with 1, 0 again. So I hope you can see that the row space is same. Now, column space is different, however, because what is the column space of this matrix? X-axis. But what is the column space of this matrix? Y-axis. Okay. If we plot it, okay, this is row space of A, row space of B, column space of A, column space of B. Okay. If I plot it, so since this is 2-dimensional, which is nice, this is the row space of A. Okay. This is where A will lie. This is row space of B. This is where B will lie. This is column space of A. Column space of A again has just x-axis in it. So this is where A will lie, and column space of B is y-axis. So this is where B will lie. So you can clearly see that these two are equal, but these two are not. Clear, Kishore? Okay, good. Okay, so it's already 8 p.m. I just want to do one quick question. Okay, it's a very simple question, but question 4. Okay. You don't need to solve it, you can just give the idea. Okay. Yeah. Question says, suppose NA, which is null space, remember, is the span of these two vectors, which are clearly linear independent, so they form a basis of the null space. Okay. NA is the span of these two vectors. Find the row space of A. So, any idea on how to do this?
Sir, without knowing A's dimension, is it even possible?
Okay, so A is. Can you do it without using A's dimension? Try to do it without using A's dimension.
Cross 3, I know. So A will be M cross 3. That is, I'm sure. But what will be M? We can choose M as anything, no?
Exactly. How do you find M? Right? I think it makes sense. In my mind, I think you don't need A's dimension. Let's see.
Okay. Okay, I think I got you. Yeah. So for finding the row space, we don't need A's dimension, right?
Yeah, I also think the same.
Yeah, it will be one vector only, and it will have 3 components. So it will be perpendicular to these 2 vectors.
Right.
I know.
That will be also 2. Row space of A will be 2.
2 what? Just 2.
No, 2 bases.
Oh, given dimension.
Dimension will be 2.
No. I think the dimension will be 1.
Okay.
Yeah. Yeah, that's correct. Good. Oh wait.
We have to use this rank nullity theorem, no? Here also.
Yes, Satinder. So yeah, that's one hint first. You need to use the rank nullity theorem somehow.
I had the confusion in the beginning only. Due to that only the problem is arising.
Okay.
What I was thinking, what I in the notes it was there, like dimension of column space plus dimension of null space is equal to the column of the matrix.
Yeah. Okay. So
Now then it will be dimension of row space plus dimension of left null space will be equal to the row of the matrix.
Yeah, I'm sorry for the confusion. Since the ranks are same, you can not think in terms of dimension of row space, dimension of column. You can just replace with rank. Yeah, sir.
Okay.
Yeah, I think there was a message just now. Okay, we'll check that. Okay, I'll just give you, I don't know, 1 minute. Okay, for everyone to try, and then we'll look at the solution and then conclude the class.
Here, row 2 is sum of row 1 and row 3. So row 2 is linearly dependent.
That's
so
right.
Rank will be less than, rank will be 2.
Rank will be at most 2, right?
At most 2.
Yeah.
So next what we should do? I'm still thinking.
Oh, okay.
What I could find out was that row 2 is equal to sum of row 1 plus row 3.
So here, in this question you mean, no?
In this question.
Yeah, here, I mean, first part is, of course, you need to use the rank nullity. But the next thing is you need to find the row space. So if you need to find the row space, you need to use a property of the null space. How is null space related to row space?
That is ortho.
Exactly. Okay. So okay, I'll discuss the answer now. Okay, because we are first 8. Okay, so what is the idea here? Okay, so for example, do I need the dimension of the matrix? I don't need dimension of the matrix immediately. So what I can see is, of course, I'm talking about the span to be a 3 column. There are 3 columns here, right? So okay, wait, it's better I write it in this way. So what I'm given is NA is the span of this 1 1 0 0 1. Okay. Now what do I immediately see? There are 3 rows. Number of rows is 3. Right, there are 3 rows. So, okay, at least that I know about A. Okay. The next thing I have is that this theorem that the nullity, which is nothing but the dimension of, the null space, which is nothing but 2 here because there are 2, and you see, observe that these are linearly independent. Okay, so this forms a basis. Okay, so plus the nullity plus what? The rank is equal to what? The number of rows, right? Now what do you have? What is this? This is 2. Now 2 plus rank equals 3, so which means rank of the matrix is equal to 1. So what does the matrix look like? Firstly, it has 3 rows. Okay, it has 3 rows. Okay, and it has a rank 1, which means
why should it have 3 rows?
it has 3 rows because you can see that the
You can have 1 row as well, no? Only 3 components should be there. Like columns should be 3 for sure.
So it has 3 components. So if it has 3 components and I'm describing it using A, I'll need at least 3 rows, right?
That's where my confusion comes in. Like so for it surely has 3 columns, that matrix, but why are you saying that it must have 3 rows? Can't it have 2 rows or 1 row? Particularly it will have 1 row if we take one example, but why can't it have 1 row or 2 rows?
No, so by 3 rows I do not mean exactly 3 rows. It could have at least it needs to be represented by at least 3 rows. Because
by 3 I can represent it by 2 rows or 1 rows only.
but what if I'm talking about span of a 3 component vectors? No. So the 3 component vectors could lead to a matrix which requires a 3rd row. Of course, if it need not always be the case. Yeah.
Are you writing A or are you writing some other matrix? You're writing capital A matrix or you're writing nulls some other matrix?
No, I'm writing capital A matrix.
Yeah, so capital A matrix, why it needs to have at least 3 rows? So it needs to have at least 3 columns for sure. Exactly 3 columns, but why 3 rows it needs to have?
No, I mean, okay, I think I get your answer. What you are saying is, since we are talking about the null space, and the null space is talking about A transpose x equals 0, and
Talking about Ax equal to 0, right? Not A transpose.
Ax equals 0.
Only Ax equal to 0.
Then all is correct. I don't see the.
Okay, sir. Let me try to express what I'm saying. So suppose A size is m by n. A is m by n size. Then the row space is a subspace of Rn, right? As well as null space is a subspace of Rn.
Yeah.
If A size is m by n, then row and null space are subspaces of Rn.
That's right.
So here it is mentioned that null space is a subspace of R3, right?
Yeah.
So n is equal to 3. I got that part. So A's size must be m cross 3.
It's some m cross 3. Correct.
Right. So A's size is m cross 3. Then it surely has 3 columns. But why do we need to have any particular number of rows? How can you say that it needs to have at least 3 rows or at least some rows? It has m many rows. You can take m as 1, 2, 3, anything. No?
But see, the fact that I am taking the fact that the null space is composed of 3 component vectors.
Right.
I have these 3 component vectors sitting in the null space, right? And the null space is a okay. Yeah, I get what you mean. It should have. Sorry. You're right. If it was A transpose, then it would make sense. Okay.
Right.
That's right. Because X is an m dimensional.
X is n-dimensional vector. A is m by n.
N, yeah, n if n is the number of columns. That's correct. That's correct. Yeah, thanks. Yeah. And but that means there is something wrong, right? Because oh no, it's correct. It should have 3 columns instead. That's correct. Yes. So A should have 3 columns. So, and this is also not left nullity, it should be nullity, which is what the question is. Oh, okay, yeah, okay. 3 columns, so rank is 1. Okay, great. So the rank is 1, meaning that A, the matrix A, okay, whatever row space it has, okay, the row space can be represented by a single vector. Row space, okay, which means that the dimension of row space is equal to 1. So which means that the row space of A can be represented by the basis of size 1, so by a single vector. Okay, now what is that single vector? Okay, that single vector, okay, belongs to A, okay, let me call it W, okay. W is in the basis, not, okay, need not be in the basis, it can just be in the row space. It is in the row space of A, and furthermore what you have that if I do W vector is, since it is in the row space, now we have that orthogonality property. If W vector, it means that W vector is orthogonal to every vector in the null space. So let me take W to be XYZ. W to be XYZ. Now I need to find this XYZ. How do I find it's orthogonal to everything? So I'll just find that it's orthogonal to the to the basis vectors, and that will guarantee orthogonality to everything in the vector space. So firstly I have 1 1 0 0 1 1. No, so it means that if I do a dot product of XYZ with 1 1 0, I have 0, and a dot product with 0 1 1, I have 0.
It will be 1 minus 1 1.
1 minus 1 1. That's what you got. Let's compare that. Okay, Satinder. So you have x equals 0. Oh, what am I saying? No. You are doing a dot product. X plus y equals 0, and then you have y plus z equals 0. Then you have what? This implies that x equals minus y, which implies that z equals minus y. So let's take x equals t. Then what do I get? I get x equals t, that's okay, y equals minus t, and z equals t. Yeah, that's right, Sadinder. So therefore row space equals the span of t common 1 minus 1 and 0, 1 minus 1 1. Okay, henceforth. Okay. Okay then. I think we've come to the end of the. Yeah, that's right. Okay. So we've come to the end of the session. Okay. If there are any questions, maybe we can quickly look at them, or else we can call it a day.
Can I ask one? Already it has been explained, but little bit doubt is there.
Sure.
For when we are solving the system of equation like ax equal to b, okay. So actually we are looking into the two perspectives. like column space and null space.
That's right.
So why we are doing this one part?
When solving a system of linear equations.
So for solving, so why we are looking for that x which corresponds to 0 every time for the homogeneous part?
Okay. Oh, okay. You mean null space?
Why we are looking into the null space part, like system of equation, so we can get by general calculation also.
Yeah.
So why we are ignoring means we are seeing that vectors which corresponds to, I think, which is mapping to the 0 1. I think it is called as the kernel.
Yeah, it's for the kernel. That's right. We will also talk about Ax equals B case. Okay, for example, if they are not consistent and so on. But we'll do that in the next week, in the coming week.
Okay, sir.
Okay, but we will look at that case also. Of course, null space is more fundamental compared to the others. Okay, and null space has some really nice properties also. That a few of the properties you already saw. That in relation to the dimension, in relation to orthogonality, and this actually comes from the general field of algebra. Okay, if you take other fields of algebra, which is not linear algebra, like for example, if you take rings and groups and all these kind of objects, then you have this idea of a kernel there also. Okay, and the kernel there is sort of a generalization of the kernel here. You get it? So this is because of a more general property that we are also studying null spaces. But why exactly Ax equals 0? Why not maybe Ax equals some other B? Things like that, we'll see it in the next week. Don't worry.
Thank you, sir. Thank you.
Okay, thank you.
Okay, sir. Good night, sir. Good night.
Okay, good night.
Sir,
Yeah.
I have just one doubt. So the previous class I couldn't attend, so I was solving the questions, and one question. Actually, the first question, it was that vector space of all functions defined in 1, 0, this interval.
Oh yeah, I remember that question had issues. Yeah, that question had issues.
Okay, I didn't see the solution actually. So till now I haven't watched the lecture.
Oh,
so,
okay. It's better you don't, because it seems when I'm framing the question, I didn't think about it too carefully.
Okay. So are you talking about the first part or the second part? Because f0 equal to 0 is pretty easy to solve.
The first part.
No problem. f1 equal to f0 was bugging me. So f of 1 equal to f of 0, that kind of functions. So
f of 1 equals, both of them don't form vector spaces. It was a very badly framed question.
But f of 0 equal to 0 is a very valid one. So why are you saying that?
Which one? F of?
F of 0 equal to 0. Or sorry, let me see that question. Just one second.
Yeah,
the question was wasn't f of 0 equal to 0. I think it was f of anything. Oh, okay. Sorry. It was f of 0 equal to 0. I was treating it as a constant value. It maps everything to 0 vector.
Oh, okay. No. It was not a constant function.
F of 0 equal to 0, right?
Yeah.
Right. Then it will have problems, right?
Yeah, it has problems. That's a very badly framed question. Forgive me for that. Okay.
No worries, sir. No worries.
Yeah. But yeah, besides that, I hope all was clear.
Sir, you yourself write these questions. Actually, they are pretty very organized in LaTeX. So later, if you have some time, give me some tips on LaTeX. That how do you do these things?
Oh, okay. Thank you. Well, I used to try to be as organized as possible. Nowadays, I am framing it in sort of last moment. So, but yeah, I'm glad that it's still
organized. Sir, very Sir, I have one doubt specifically. So, Kishore, I think he raised that point, and we are having the conversation. So you pointed one thing that let's talk about a matrix which is of size 10 cross 200.
Yeah.
So I have this matrix A 10 by 200. So one thing basically I'm trying to say one applicability of row rank equal to column rank. And
yeah.
So I can say that 10 important columns are there. Important means like 10 columns are there, which I will be preserving, and all the rest of the columns can be expressed as a linear combination of these 10 columns. This I can say from the row rank equal to column rank.
So see, the thing is that
what I'll be doing is,
continue.
no sir, just one second. Yeah. So now, when someone is interested to look at the row space, they might say that, okay, Rohan, you have selected A from 10 cross 200. So the row space is all the operations that you want to do. They should be done in R200, right? But what so the applicability lies here. What I will be telling them is, you don't need to go to all R200, all the row space. You only go to R10, and I will design that R10 in such a way. So I will say that number of independent columns is 10 only. It is 10 by 200 matrix. So can you just write it? It will be easier for me to visualize them.
Okay, sure.
I also don't know whether it can be done or not. That's why I was discussing it with you.
Yeah. Tell me. So this is what you're interested in,
10 cross 200.
So it's like n cross 200.
So it is a rectangle.
10 cross 200
kind of matrix.
10.
Right.
Okay.
So a very lengthy kind of, right?
10 cross 200. Okay. So
now,
more columns.
When someone wants to perform operation on the rows, they are thinking that they have to do operation on R200. Right?
Yeah.
But what I'm telling them is, here the row space is isomorphic to R10. Can I say that?
Row space is isomorphic to
R10.
R10. What is R10?
Like R10, 10 many components, R3, R2, R3, R10.
So row, you mean?
Your numbers raised to the.
You mean like R10?
R10. No, sir. No, sir. Like R3, no? 3-dimensional plane.
Oh, that. Okay. R, capital R, real numbers. Okay.
Capital, yeah.
Okay, yeah.
Right. So when someone is saying that to perform row operations, they should be considering R200. I'm giving them an alternative, and I'm saying them don't perform operations on R200. It is playing. It will involve playing with many numbers. Instead, play with R10, and I will give you the mapping. And so, can I say that here the row space is isomorphic to R10 at first?
See,
because they have dimensions in it.
I mean the issue I have is like, what you want to do is you want to replace a row operation by a column operation. Is that true?
No. I'm trying to figure out if I don't consider this 200 components in each row, and if I'm considering only 10 components in every row, can I have the exact same or similar kind of operations that I could have performed in R200? When I'm saying R200, it is capital R200, okay?
Yeah. So, what do you mean to say? Okay, see, still, I'm not sure I completely understand you. What you mean to say is that, see, if you look at the columns of the row, the maximum that they can span is R10. And if you take out the rows, then the maximum that they can span is 200. Yeah?
Okay, sir, let's do one thing. Let's have a very simple 2x4 matrix. Then I will be able to say.
Okay.
2x4. And can we just write it quickly?
Yeah.
Just the first row only. Can you write the first row only?
Sure. What do you want?
A11, A12,
okay.
A13. Right. It's 2x4, no? So
2x4.
We have 4 components.
So 4
components.
Right.
Yeah.
A13, A14,
exactly.
A24. Okay.
Awesome. Yeah. So, sir, now when someone is saying that for playing in row space, they need operations in R4.
Yeah, that's right.
Yeah. Instead, I'm saying that look, here at most the rank can be 2, right?
Right.
At most the rank can be 2. So I'm saying that the row space is isomorphic to R2 because their dimensions are same. And I'm going to now someone will say, how can you establish isomorphism? I will give them a mapping.
Okay. I get it now.
So since they are isomorphic, and if we can find an exact operation, now the main challenge will lie in, you will say how you are going to map
it. Yeah, that's right.
But if they are isomorphic, one thing is guaranteed, existence is guaranteed, right? That there exists a mapping.
there exists a mapping. Will you be able to find that mapping? It's a very interesting question. Has a very nice computation flavor to it. So what you have is anything that you can do in R10, you can do it in R2. Sorry, R4, you can do it in R2. Basically, that's what you mean.
Yes, if we know the operation.
To be a mapping.
And the idea how I will be mapping is I will map these two linearly independent rows to the two standard bases of R2.
That's sort of what I was also thinking. That I do not see a way of not like computing linearly independent rows, because what you want is you want to find the basis and then work only with respect to those bases, right?
Right.
For example, if you have 200 rows, then you want to find a basis of size 10, and say that when you are accessing a basis of, if you are accessing a vector of size 100, then it can be broken down into 10, maximum 10 many bases. In fact, you are saying that even the bases have dimension 10. For example, in 10 cross 200, you can at most have 10 bases, and if you want to do an operation, then.
So, is it possible that I store all the information? So, I don't want to truncate. So, I want to store, maybe a number of coordinates will get reduced because I'm mapping it to a lower Rn. So, but can I still hold all the informations?
It depends on like how much resources you are given. So, for example, like, are you talking about efficiency in terms of space or time? What you are trying to do here is probably probably save time, right?
Okay, I was thinking about space actually. Instead of storing these 200 components, can I store them in 10 components? So,
you're talking in terms of saving space.
Right.
Okay. I mean, that's a very interesting question. I think the exact problem statement is now clear in my head. Okay, we'll think about it offline. And
okay, sir, sure.
If I think of something, if you think of something, then we'll discuss it in the next session. Is that fine?
Sure. Yes, sir. Yeah.
But yeah, very nice that you brought this up. It's an interesting thought. Okay, then I think we can conclude the session.
Yes, sir.
Okay, thank you, Ron. Okay, thank you.
Sir, Mr. Shivkumar has something to say, I guess.
Okay.
Just say bye and happy Navratri to you.
Oh, yeah. Happy Navratri to you. Yeah.
Thanks, sir, happy Navratri to everyone.
Yeah. Happy Navratri to everyone. Hope everything is fine in this festive time. Yeah, actually, I may also have to go during the time home, so that's the reason why it may get shifted the next session. I'll get the information and then
change the time in the next.
Yeah.
Yes, sir. So if you change the timing in the next week, it will be helpful for us also. Like it will be puja session here.
Oh yeah. That's right.
So
that's right.
Yeah.
Probably I shouldn't hold it on the day of Dashera. Yeah. It should. Probably the weekend or something. That's what I was thinking. Weekend will be bad. Maybe the next Friday or Saturday. That's I was thinking in my mind. Okay.
Okay, sir.
Okay. Yeah. Thank you so much. Happy Dashera. Okay.
Good night.
Good night.
Happy Dashera.
Okay.
Good night.
Good night.
Good night, sir.
Yeah, good night. Bye.